I thought I'd wake you up with a lot of movies, so please be awake and don't fall asleep. I see you, so don't do that. The topic is understanding dynamics of multi-fault earthquakes. I'll talk about small earthquakes, large earthquakes, and how we can use supercomputing, fracture mechanics, and highly interdisciplinary observations to inform these models and to validate them. And let's see. So this is an outline. Since it's a school, I start with a short introduction to dynamic rupture simulations, including a few examples. For example, yet another dynamic source inversion of the 2004 Parkfield earthquake. Then I talk about a recent paper where we've been argumentatively argue that fracture energy might be fault size dependent, and that can explain cascading earthquakes in multiscale fault and fracture networks. And while I'm going through this, I will also show some recent rupture dynamic simulations of the Turkey, Madhu, and Ridgecrest earthquake sequences. In the third part, I talk about the 2024 Noto earthquake that Kato-san was introducing to us on the first day of the workshop, and how multi-fault complexity is governing tsunami generation, and which aspects of rupture complexity actually matter if we are maybe only interested in better understanding the generation of tsunami. And lastly, big computation and ML, and do we need ML or not? While I go through this, please feel free to ask questions. There's a lot of very different topics, so please interrupt and ask, because probably at the end of the talk, we will be at a very different stage than we were at the beginning, hopefully. I do it like this. Okay. So what's a dynamic rupture simulation? The key point is there with an asterisk. It means that the earthquake dynamics are not predetermined or prescribed. They evolve as a consequence of the model's initial conditions and the way a fault yields and slides, controlled by an assigned friction law, relating shear and normal traction on friction interfaces. And all of this is nonlinearly coupled to seismic wave propagation. So we're treating earthquakes as frictional shear failure of brittle solids under compression along pre-existing weak interfaces. And much of the complexity that you will see in these models lives in the definition of friction. We heard about, a lot about that, but also in fault geometry. And we started to hear about this in the beginning of today. What you're seeing here is an example of such a dynamic rupture simulation. This is one of a suite of models that informed physics-based probabilistic seismic hazard assessment in North Iceland. And this was the fault system geometry that we were able to incorporate in these models, and then try to understand, does all of this heterogeneity in fault structure actually limit, for example, the maximum possible magnitude that this fault system can host, which is a very important parameter for PSHA. Fracture mechanics is not the same as dynamic rupture simulations. In fracture mechanics, we also can treat we can also describe the frictional failure of brittle solids under compression that initiates earthquakes as propagating shear fracture, so far so similar. However, fracture mechanics formulations are mostly unsolvable analytically as soon as it gets a little bit interesting or a little bit more heterogeneous or geometrically more complicated. However, the theoretical framework of linear elastic fracture mechanics has been very successful. We've seen a couple of examples throughout the school so far. One of the aspects that I will touch upon today is that it has been adapted to describe an energy balance that governs how earthquake rupture grows in idealized settings. And traditional in LEFM, we consider that all material parameters are given and they're scale independent. And that in turn also means that fracture energy should be scale independent, and I explain that again in more detail later on. So there's a recent community review perspective by David Kammer. Many of the people here were co-authors that explains how earthquake energy dissipation and the earthquake energy budget can be described in a fracture mechanics framework. This is just one figure from there, where you can see all of these interesting processes, what happens at the rupture tip, what happens at the tail, how does this relate to the seismic waves being radiated and the energy being consumed during earthquake rupture. In dynamic rupture simulations, we couple seismic wave propagation to a dynamically running shear fracture on a frictional interface, and that frictional interface can be itself embedded in a rheological continuum. We've seen a lot of models that were looking into elastic, purely elastic media and how waves propagate there, but we can actually include viscoplasticity, you've heard that, but also anisotrope and poroelastic media that have more complicated effects on wave propagation. So all of these models always solve the seismic wave equation. So everything that you will see is nothing more than a hyperbolic PDE solver stepping through the wave equation. This has advantages. We can use explicit time stepping, as Brittany explained, which is good for getting that on large supercomputers. There's a lot of techniques, numeric techniques and algorithms around that help us solving a hyperbolic PDE. And then we're adding additional ingredients, fault friction, nonlinear off-fault rheologies, thermopressurization, additional equations that we can solve. This problem, even in its simplest form, is highly nonlinear. And this is because what happens on the fault, this internal boundary condition in terms of contact and friction, is nonlinear coupled to the seismic wave propagation that is solved for in the continuum. So even though we're everywhere solving the seismic wave equation, we're adding a boundary condition here, the whole problem becomes highly nonlinear, even if it's in its simplest settings. And this explains why it's challenging, for example, machine learning algorithms. And then the evolving displacement of this fault along this fault is what we call slip, and then we're studying the dynamics of this slip during earthquake rupture. Typically, these faults are treated as infinitesimally thin surfaces. They always stay in contact. They do not open typically, and this is part of the boundary condition that is prescribed here. So solving these kind of models with high-performance computing has been a big success, and partly because we could bootstrap on decade-long developments in computational seismology. So the seismic wave equation has been of interest for many decades and has been solved on large computers. And we can use these efforts because we're also solving the wave equation, as I just explained. And a common approach is that we seek solutions in the time domain. So how does our wave field evolve from one time step to the next one? We solve this in a parallel sense by domain decomposition. This is why, for example, here you see our globe being split up in many tetraeders, so triangles in 3D. And each of these little mini domains gets assigned to one of the ranks, so one of the CPUs or one of the GPU threads, and they're solving this by itself, and they communicate either in local or in global ways, depending on the numerical algorithms. These kind of methods have been implemented in finite difference, finite element, spectral element, and discontinuous Galerkin methods. There's different ways how to get the rupture in there, for example, via split nodes or numerical fluxes. I can talk a lot about this, please ask me. I don't have too many slides, but I'm really happy to talk more about this if you have questions. So what I wanted to say here is that we're using large supercomputers, also with these more complicated dynamic rupture models. This is one example that competed for the Golden Bell Prize in 2014. So this is something like the Oscars of computer science. You know, all the different groups compete first to get access to largest machines, then you have to prove that the code scales up, and then you have a very short time window to run a large simulation where you get the full machine, and then you write it up, and then you compete for this prize. It includes engineers going down in the big computing halls with ice packs cooling some of the misbehaving cores, and it's quite hands-on and quite exciting. So we are able to use these big machines, and it is, I would say, a curse, but it's also in the sense of the barrier that it causes, because to run these models at this scale, you do need access to one of these machines, but it's also a big advantage because these machines exist, they're funded, they're national research infrastructure, and as geoscientists, we shouldn't leave these machines just to the biologists, but we should also be able to use them to solve our problems, or the astrophysicists, even worse. Okay. So they do use the largest supercomputers worldwide since decades and today. For example, 2 seismology codes in a protest sense. I saw our code and AWP also from Santiago have just been re-announced to remain part of designing NSF's next exascale supercomputer. So exascale means that these machines are able to perform 10 to the 19 computations per second. And there's a lot of other infrastructure efforts focusing on training. So we have a recent preprint here Yeah, was led by Marine Denol, of how you can run these trainings, also including cloud computing and getting access to these machines. We have a science gateway that allows you to run these simulations just in a browser window without understanding much about how to have to log in these machines and so on. We have these regular cyber trainings. I don't have one here, I did one last time, but the next training I'm running is in a month from now in the Netherlands, where the weather will be much worse than here, and the food probably too. But that's what I signed up for. It's part of the TRED ITN. Okay, so back to simple models. We've seen that even quite simple 2D linear elastic models reveal quite complicated earthquake dynamics. So this is one of the first dynamic rupture simulations published by Okubo in 1989, rate and state friction simulation with slow quasi-static nucleation and then fast dynamic rupture. Here's another example where you nicely see super shear rupture illustrated. So 2D rupture dynamics models of a super shear rupture. So super shear means that this rupture frontier is propagating faster than the S-wave speed of the waves in the surrounding material and is thus stacking up waves in a Mach cone similar to an airplane going through, breaking through the wall of sound. So we can have different rupture speeds, subshear, supershear ruptures. We can have different rupture styles, pulses and cracks. We can have slip reactivation, back-propagating rupture fronts. Here are more examples. This is work by Yihe, where they showed that pulse-like ruptures can be induced by adding a low-velocity fault zone in these models. This is work for my PhD with Pablo, where we showed how rupture styles can transition from decaying pulses to growing pulses to cracks from subshear to supershear, depending on nucleation and relative fault strength. And here's another example that I will get back to when I talk about the Noto earthquake, about slip reactivation. So these kind of plots are very common when we're discussing dynamic rupture models. What you see here is our line fault, so it's a 2D model, and then what's stacked up is the same fault at different steps in time throughout the simulation. Here's the slip rate, so dark means fast and light means slow, and here's the shear stress change. And what you see here is a pulse-like rupture, right? You have your rupture front, you have some slip, but then it heals again, it's a growing pulse, the area of slip gets a bit larger. And what this pulse is doing is that it's reaccumulating, redistributing stress in the hypercentral area here, which eventually leads spontaneously to reactivation and re-rupturing of the same part of the fault. And this secondary crack, right, this is a crack, can itself cause a supershear transition here. So at the end you have 3 rupture fronts, a subshear pulse, a supershear pulse, and a third subshear crack. And this is a very simple model. The only ingredient here is that it's fast velocity weakening rate and state friction. And there is really nice analytical work that preceded these simulations by Niels and Madariaga that come up with a steady state pulse solution that describes the stress reaccumulation of a pulse-like rupture at the hypercenter. And this is one example where you could interpret that this is something that happens in nature. This is a slip inversion of the Tohoku earthquake. You see slip rate, so the speed of slip, and the slip evolving here. And you can see 3 episodes of rupture propagating away from the hypercenter during the same event. Last introductory slide here. You've seen some examples that these kind of simulations can go beyond interface-only friction. The community has been very interested in including more interesting and physics-based off-fault interaction of these propagating ruptures on faults. I just built up this slide. And there's been really a variety of rheologies that has been used. So this is a work by Kurama that he introduced already, where you have explicit fractures that resemble microcracks, ring cracks, and these are modeled by allowing a mesh and the interface of that mesh to spontaneously break. This is a very different beast. So this is actually hyperelasticity, a crazy hyperbolic PDE system. It's not much to do anymore with the elastic wave equation, but it models a mesoscopic shear fractures evolving during rupture. A phase field model here, and this is the classic Drucker-Prager continuous plasticity, however, combined with a quite complicated dynamic rupture model of the Landers earthquake with complicated fault geometries. And what you can see is that even with this very simple rheology, like a geodynamicist would probably kill me for even calling this plasticity, you can see that you have strain localization, mapping out faults that were not part of the model, but were actually probably existed in nature that we didn't include in the first place. So you can get interesting effects even with simple rheologies. So these models do not have to rely on purely artificial initial conditions, but we can use a range of observations to inform them and also to verify them. So we're able to include geology. This is the fault system of the Cargèse earthquake, 3D velocity structure, topography, stochastic, if you want, or fault roughness, descriptions of the initial fault loading, friction experiments. You combine all of this in meshes that can be capable of representing all of this complexity. You can solve for seismograms, ground deformation, but also more maybe exotic outputs, such as acoustic wave propagation in the atmosphere that could be linked to loud sounds that earthquakes make. We currently have a collaboration with Yoshi where we are linking this output of these models to the electron count in the ionosphere, to tsunami models, and of course what we're interested in today is to learn more about fundamental physics. Okay, so what can we do with the output of these models? Here's just one example, work by Nico Schlieber, where we're showing, okay, so one of the advantages here is that we can generate incredibly dense synthetics. So for example, the map here is synthetics out of 1.8 million virtual seismic stations. And what you see is the corner frequency, so the near field corner frequency, as it would be measured by all of these stations around a dynamic rupture model of the Ridgecrest earthquakes. And you see a lot of variability in the corner frequencies here. And this is linked to these very sharp vertical pulses in ground motion. But it's highly localized. It really looks like, back to astrophysics, it looks like star strike patterns or some kind of explosion. And only part of this is linked directly to the radiation pattern, and other parts of this are directly linked to earthquake physics. And better understanding this very local variability is important for hazard, but it's also important to inform us what to look for example, in DAS data, which is can be similarly dense and low frequency. So the frequencies here are relatively low. You don't need a high resolution model in terms of time to come up with this. To better understand what we're seeing here, we did isochrone analysis, so tracking back where these pulses are coming from. And I just make it very short. We see that this is caused by rake-rotated surface breaking rupture fronts. So this is a strike slip earthquake, however close to the free surface. And Yoshi also has interesting work on this in simpler models. You see rake rotation, so you have rotation of the slip direction while this earthquake is breaking to the surface, and that can cause really impulsive and localized strong velocity pulses here. I included this slide just from listening to the workshop. These dynamic rupture models can be linked, for example, to slow slip cycle models. This is a recent study we published last year, and the editor wrote this editorial piece, and I put this question mark there because that's actually not what we said, that we can forecast earthquake rupture from slow slip evolution, but it's going in this direction. So we were interested in the 2014. Sorry if you were the editor, but we were interested in the 7.3 Guerrero earthquake that was in Mexico, that was preceded by a slow slip event. And that's really a unique case study to better understand the physics linking slow slip events to megathrust earthquakes. So we built up a dynamic rupture model that's matching the observation we have available. And then we tried to see, is any of the preceding slow slip events able to trigger dynamically or activate or initiate that earthquake? I wanted to play this movie. So these are the slow slip cycle models, and they can be constrained by long-term GPS measurements. And what we find is that accelerating slow slip fronts transiently increase shear stress enough to actually initiate this earthquake and also increase its complexity during propagation. However, it's not enough to just look at a single slow slip event. We really had to model, in this case, 4 of these slow slip events and how they redistribute stresses across the slab to be able to understand why, or come up with an explanation of why this 2014 event might have been the one that triggered that earthquake. So these accelerating slow slip fronts transiently increase shear stress at the down dip end of the seismogenic zone. Also the geometry is interestingly complex in that area. There's a flat slab. And the main key message here, you can see this acceleration in these plots. And the key message is that it's really important to analyze the long and the short-term interactions. So don't not only focus on a single slow slip event coupled with a single earthquake, but really look at the same slab and its full fault slip spectrum. And the last introductory example is that we are not stuck with forward models. We can actually look at this in an inverse sense, at least with simpler forward simulations. And we have a recent dynamic source inversion of the 2004 Parkfield earthquake and 3 months of afterslip. So this has been attempted before, which makes it interesting, also a little bit challenging. So what we do is we invert for spatially variable pre-stress and the friction law parameters in a joint forward model. So it's dynamic rupture plus 90-day post-seismic deformation. And what you see is one of the preferred models of the rupture dynamics and the afterslip evolution. This is the total of 2 million forward models. So this is in the range of millions of forward models we need. And that cost around 60,000 GPU hours, which is a lot. So it would be good to speed that up. Okay. So this is the preferred co-seismic model. And I just highlight the interesting parts, or the new parts that we can learn from this. First, there's 2 very distinct rupture phases that are actually spread out by quite a lot. We see the rupture duration being quite a bit longer than other models that have been proposed before, even though this is one of the best studied events around. The first part of the rupture is a pulse-like phase, which is mostly visible in the seismic data. The second part of the rupture is a crack-like phase, which is mostly important to match the co-seismic GPS data. And then there's some abrupt rupture speed change here that could explain local high-frequency sources that have been analyzed before. And in general, this agrees well, besides this longer duration. And it's quite interesting to see this unexpected behavior, strongly radiating pulse and a not radiating crack. Yeah?
Did you make it stop by having a velocity strengthening patch at the top?
No, the model inverted for that. The model inverted for that.
That's what you found.
Yeah, so this is part of the inversion, how rupture stopped. And I get to that, actually, in the next slide.
I have a question also about your source time function.
Yes.
So I see that you have 2 peaks.
Yes.
And it seems that your peaks are asymmetric. Where does it come from?
It comes from the quite heterogeneous, you see the heterogeneous stress drop here. So it links already to the heterogeneous, there's a lot of heterogeneity that the model needs to be able to fit the data. A caveat here, the forward model is simple, it's just a planar fault. There's no fault zone also, so it's really, the forward model is quite simple. So a lot of the complexities that we might miss in setting up this model are mapped in very large heterogeneities, and I have this in a slide how this looks like, but this is why. Actually, the onset of this earthquake is really fast. This is one of the reviewer questions, if that's realistic, but it's interesting to see that. Fast velocity weakening rate state friction for. Yeah.
Inverting for all the parameters?
We're inverting for. I thought I had this. Yeah. Okay, so spatially variable pre-stress, A minus B, the difference between F naught and F weakening, in this case L, and then the initial slip rate and the weakening slip rate. This is something that has been adopted before, just not to the Parkfield earthquake. There's another paper by Jan Premus where they used this for one earthquake in Turkey, but I'm not a co-author. Can't say much about that one. Okay. Now, it starts to get interesting if you're also looking at the afterslip evolution, because what happens during the earthquake imprints directly on the afterslip kinematics. And you see here an animation. So the first thing is, this is not a boring afterslip front that is just filling up everything that didn't slip. This is something that has its own kinematics, interesting, speeding up, slowing down, going through asperities. And in addition, it has a memory of what happened during rupture. So if rupture arrested either at the strength barrier or the velocity strengthening friction barrier leads to very different after-slip evolution. And well, if rupture propagated into a velocity strengthening region, you get a lot of after-slip being generated there. If rupture is stopped within the velocity weakening zone, just as an asperity, you will not get after-slip evolution there. So it could be really interesting fingerprint that we could start looking for to also learn something about the co-seismic rupture. So for example, there is, let me see, this backward propagating after-slip front that you see here. This is a part of the model which is not super well constrained, but it does align with delayed aftershock activity, so we have some confidence of leaving this in the model. We also have a pronounced after-slip gap, where co-seismic rupture strongly decelerated, so this is around here. So there seems to be a barrier that is visible for both co-seismic and after-slip. Yeah.
Can you show the movie again?
Yeah.
Because your after-slip seems to start where you have the co-seismic rupture. Can you explain this?
Yes, so everything where co-seismic rupture, it penetrates into the velocity strengthening area, and this is where also after-slip starts first. It's the same inversion. Yes, it's not. We're inverting for one set of parameters that has to explain both the co-seismic observations and the 90 days of data afterward. Yeah. Okay, and the result of the inversion is complicated. And keep in mind, the Bayesian inversions, we have a full ensemble, but this is just one of the preferred models. Shear stress heterogeneities, B minus A distribution. L is actually not as heterogeneous here, so just a couple of interesting parts. So the same dynamic model parameters drive co- and post-seismic slip in this inversion. We have highly variable pre-stress with a very strong concentration around the hypercenter. Co-seismic rupture penetrates into shallow velocity strengthening regions and causes a lot of afterslip there. We have a very low co-seismic average reference friction drop, 0.06. This is partly due to the friction law we're using. And initial slip rates within the velocity strengthening region resemble the plate rate. And there's more in that preprint. Oh yeah, and I shouldn't hide the data fit. So the co-seismic and post-seismic GPS data is good. The strong ground motion data fit is moderate, so we have a variance reduction of 0.42. This is likely caused by not including a fault damage zone, which we know exists in Parkfield, and maybe also not including side effects, even though we're in low frequencies here. Okay. Any questions so far? Yes.
You have a very low friction drop on average.
Yes.
Which means the shear stress during slip was extremely high.
Yes.
They were like tens of megapascals, 20, something like this. The slip rate is also high, right?
The slip rate is very high at the initiation of rupture.
And so it means okay. The question is, in what width do you have to distribute that energy so that the thing doesn't melt the entire plane all the time?
Yeah, that's a good question. The forward models do not include off-fault damage. They don't include thermal pressurization. I think there's a lot of knobs. You could repeat this, adding more realistic physics, and then see what the output is.
I don't
Yeah.
see it in a critical way.
No, I think you're right.
I'm trying to understand to which extent we can believe that indeed the shear stress was high during slip. Because that would have released a lot of heat, like tremendous amount of heat. So I'm just trying to think if you have done those calculations, just back of an envelope to see whether
Not yet, but
have to have
I
like
can check.
10 meter wide zone or meter wide zone.
Yeah.
Because that has some consequences.
Right. That's a good point. Chris?
So we can save this until later, but in case you have some slides to talk about the trade-offs in your model between things like A minus B and L, or even the friction drop, and so it seems like there'd be some fundamental trade-offs between those.
Yes. I don't have the slides, but it's in the paper. And that was one of the key things we were trying to find out. Can we see correlations? I don't have a strong story, unfortunately. But we can discuss this later. I can show you all the correlations. It's not revolutionary, unfortunately. No.
So you mentioned that the high stress is concentrated at the nature capsule.
Yes.
So is there any observation constraint?
We argue that there is, but yeah. it causes a very rapid onset of rupture, which is something we argue that you might see this in some of the seismic observations, but yeah.
Just a very short one. When you're showing the results of the MCMC
Yes.
model, is that the mean model, the map?
It's the model that reduces that most reduces the variance. That's what we chose in terms of the data misfit.
Are there several modes in the distribution, or?
Oh yeah. Also, I'll show you later. That was just the introduction. So now we get to the real stuff. Okay. Second part. Okay. We've heard that faults and fractures are multi-scale systems spanning millimeters to thousands of kilometers. So think about the scales. All of them are seismogenic. Like small fractures and 1,500 kilometers long subduction zones can host earthquakes spanning magnitude -4 to 9 observed in nature. And they all seem to be following the same physics, but the scaling is being debated. We also know that all of these earthquakes and small lab quakes reveal a striking variability of earthquake dynamics. So here's some examples. Intermittent lab earthquake rupture sequences and fault gouge. This is work by Rubino and Nadia Lapusta. This is actually how a damage zone can look like. So this is a poor student of Tom Mitchell mapping it all out by hand, I think. Which is very impressive. And a 3D dynamic rupture model of the Ridgecrest earthquake sequence, all illustrating this point of variability of earthquake dynamics. And we also know, now that we observed a few recent large earthquakes, that many of them are not only cascading across multiple faults, but also include multi-event earthquake sequences across geometries that are quite complicated. So for example, the Ridgecrest fault system, the Turkey earthquakes, fracture networks and damage zones on the small scales. So the first example to motivate this study, what you see here is a dynamic rupture model. I sped it up a bit of the 2019 Ridgecrest earthquake sequence, where we're explaining the dynamics of the two largest earthquakes that broke through the same fault system by apparently weak faults, so dynamically heavily weakening faults due to severe velocity weakening friction and elevated fluid pressure. And what you see here, this is maybe addressing Chris's question, is the heterogeneity of R, so that's similar to the S ratio. And these kind of ratios are really what drive our dynamic rupture models. So it's a measure of the dynamic rupture fault strength, the ratio of the maximum possible stress drop over the frictional strength drop. So this is one of the parameters that we do have to get right to match observations. We don't have to know the absolute stresses. We don't have to know the absolute fault strength. We don't have to know the absolute value of normal stress, but we do have to know the ratio of the maximum possible stress drop and the frictional strength drop to get the dynamics to match observations. Similar for the 2023 Turkey earthquake doublet, we came up with two dynamic rupture models that are talking to each other, so they're linked in terms of their dynamic and static stress transfers, even though it's not a seismic cycle simulation, but they run in the same fault system. And we modeled the complexities of this earthquake quite differently. This is using simple linear slip weakening friction. The models have higher fault strength, so we don't need this extreme dynamic weakening. And in this case, we restored the cascading potential by local stress and strength heterogeneity, reflecting the very complicated regional tectonics. So you see a lot of stress rotation here. We did some new stress inversions to constrain that. And we show that actually with very simple friction, we do account for fault geometries and regional scale heterogeneity. You can also explain to first order these complicated dynamics. Sorry. Yeah, don't do like me. Don't look at my. This is all important. Okay. This is actually all screenshots of your work that you showed so far. Okay. Okay. So some of the complexities include the delayed backward branching or the unilateral supershear rupture of the second earthquake. So as I just said, simple frictional behavior can give rise to distinct co-seismic slip characteristics, so the delayed multi-fault earthquake cascading of both events when combined with these complex tectonics and fault system geometries. For example, the mechanism of this delayed backward propagation due to dynamic unclamping at this intersection. But one of the main questions when looking at these two models, as dynamic rupture models, Ridgecrest earthquake sequence, Turkey earthquake sequence, quite different parametrizations. It's not clear what drives these dynamic earthquake rupture cascades and how do these faults talk to each other. And also remained unclear of what happens if we want to model also smaller faults, right? Because in dynamic rupture simulations and seismic cycle simulations, we're prescribing DC, we're prescribing fracture energy. And that means if you're using a too large value to be able to save some computational cost, we actually can't model small magnitude earthquakes because they would never nucleate. So it's actually quite challenging and hasn't been done to include all of the different sizes of fractures and faults that exist in a single model to try to better understand how they interact. Okay. Another recent example, so this paper just came out 2 days ago. So we're studying the Maduro earthquake. In this case, it just adds to kind of these open questions. In this case, we're modeling the non-typical unilateral doppel onset supershear transition with fracture energy variability along this fault system, which might be linked to differences in fault maturity. And we can see some really interesting patterns of that dynamic rupture complexity in fault zone optical image correlation. So for example, we might see a geodetic signature of supershear transitions in the optical fault zone width. Okay. So what is this earthquake energy balance that I talked about? This is another figure from David Kammer et al.'s review. Don't be confused by this rupture opening here. We're still in the earthquake framework where we're only looking at shear fracture mostly. And it explains this earthquake energy balance here that describes every state of how this rupture propagates, how much energy is consumed during this propagation, and how much energy is available to be radiated in seismic waves. And as I said before, despite the large number of observed earthquakes, the scaling and partitioning of the earthquake energy budget remains debated. This is one more complicated way how to plot the earthquake energy budget. What you're seeing here is a G, so this is our fracture energy. There's all kind of other ingredients that are important. And maybe I just want to highlight that the fracture energy balances the release of potential energy with several dissipative mechanisms. Each of them is interesting. And it really affects all aspects of earthquake rupture, nucleation, propagation, arrest, and what happens in the next earthquake, and so on. However, and I recommend Rachel Abercrombie's paper in 2021 for that, only a part of that fracture energy is actually seismologically observable, and that with considerable uncertainties. And that is what's typically called G prime. And G prime is only a part of G. However, a lot of the observational studies that are looking at stress drop, looking at fracture energy or seismic efficiency are blind to some parts of the fracture energy. Other parts that are invisible include, for example, co-seismic fault weakening and re-strengthening processes that we discussed at length, but they remain for real earthquakes largely undetectable. These two quantities are only equivalent when there's no stress under or overshoot. So this is what happens here. This is co-seismic re-strengthening, causing this to be not ending up at the same level here in terms of shear stress. And you could also think about this line continuing in this direction. The total G, total fracture energy, has been, in previous work by Dimitri, estimated to be an order of magnitude larger than what we see. So an order of magnitude larger that's missing. So that would be a non-negligible difference. And that's also a common characteristic of more realistic earthquake models from analytics and rupture dynamics. This is a plot from Vieska and Cargèse where they show that fracture energy scales with slip. So observed fracture energy increases with earthquake size and slip. And there's two debating explanations for that, competing explanations for that. Either continuous co-seismic weakening due to the most popular thermal pressurization of pore fluids or flash heating driven by rapid shear heating of saturated fault gouge, or the other hypothesis, fault properties such as fault size, fault maturity, fault rheology, friction parameters, heterogeneity, in pre-stress could also explain that increase of what we observe as fracture energy with earthquake size and slip. And these are, as you can see, they typically don't go together. Once a fracture energy is a fault property, once it's something that continuously changes due to thermal pressurization. Oh yeah, and then if you plot out, this is an appendix, fracture energy with source radius, there's actually quite a mess here. Now, this paper proposes that, well, these previous explanations may be difficult to unify and to generalize. In addition, they don't explain why we have small earthquakes. Specifically, thermal pressurization cannot explain the nucleation of small events, and it wasn't designed to do that model. So we explore the possibility that not all earthquakes are driven by the same mechanism, but that fracture energy might be both a fault property and a fault invariant quantity. So that would mean that you have two fundamentally different fracture processes, a small slip one and a large slip one, that dominate. They're always there, but they dominate either small or large earthquake rupture, and importantly, how they interact dynamically, and how we maybe can explain these earthquake rupture cascades. So to get to this, we developed a new analytical quantification of the difference between what's observed in the real fracture energy, and we use that difference to correct the observational inferred G prime of small earthquakes. And we do this with two different analytical models to show that this is not dependent on the specific assumptions that you do. So we have then a full fracture energy from observations plus a correcting factor here that comes from analytical physics-based models. And this is just one of a visualization of the underlying physics that defines one of these analytic models. So the models are either 3D circular cracks with flash heating friction and re-strengthening, or bilaterally expanding kinematic pulse-like rupture with stress recovery. That was published before. One of them was published before in 1D. We do assume separation of scales between the rupture tip and the rupture body. But by analyzing the stress distribution and the slip history during rupture, the analytical expression for this difference actually reveals something quite surprising, is that you get a linear scaling between the difference between observed and real fracture energy that you see here with R, which is the size of the rupture. So the average G star, the difference that is difficult to observe, is linearly dependent on the rupture size. And this result is independent of rupture propagation details. And this difference becomes increasingly important for small events with small stress drops. You can ask me about this later too. I'm just speeding up a bit. So as I said, we use this to re-estimate the full fracture energy for small earthquakes. I wanted to show this table because it might be useful for others too. As part of this exercise, I went back to a lot of dynamic rupture models and of previous small and large earthquakes from our group and from other groups. And we computed the total G, and we added that to an updated scaling. And how this looks like is like this, fracture energy and ruptured fault size. So before, this was quite messy. Now we're adding this correction of the potentially missing fracture energy, and you find a linear scaling of fracture energy with ruptured fault size up to a certain saturation scale here is where this large slip processes would be dominant. So what does this mean? This is consistent, of course, with the analytical scaling that we developed that was put into this. However, this re-estimated fracture energy doesn't scale linearly anymore with fault slip. So now we're plotting the famous plot again, small earthquakes, large earthquakes, fracture energy, co-seismic slip, and you observe a break in scaling here. And that break in scaling is the signature of where fracture mechanics have a break in scaling as well. And this is kind of where these two competing mechanisms are dominant either for small slip or for large slip fracture processes. So again, as a reminder, the small slip minimum fracture energy is a fault property linked to the ruptured fault size, dominates faulting at small slip scales. The large slip and possibly fault invariant part of fracture energy increases continuously with co-seismic slip. And here, with these parameterizations around 1 centimeter of slip, you would observe a break in scaling. That does depend slightly on the dynamic stress prefactor we're including in the analytical model, but we show also in the paper that this is not an artifact of a specific data set or specific seismological techniques. And that is something that's potentially observable. However, the slip scale of 1 centimeter is quite challenging to get to observationally. So please check and prove us wrong if you want, but this is kind of a challenge for the community to see if this could be something you could back up further. So it's a testable threshold in coseismic slip beyond which mechanics of earthquake rupture fundamentally change. So what could be the underlying mechanism? It could be localization. So this is a very similar plot to what Oke showed this morning, where you have fault unit thickness, either fault zone or principal slip zone, how this scales with fault displacement. So we compiled, I realize now, after Oke's talk, there should be lots more references here, probably, that we could add. But this is observations that suggest that the thickness of fault zones and the thickness of the principal slip zone both scale approximately linear with fault displacement. However, they both saturate. So this is a motivation to potentially explain this break in scaling with localization processes. And this is work in progress, led by Dimitri, that develops the analytical model for that. Localization of slip within fault gouge that leads to fracture energy partitioning, and that can explain exactly that kind of scaling that we observed in our correction of the seismological data. What are the implications of that? Well, we use this scaling of fracture energy to model rupture dynamics of a main fault embedded in a fracture network in the fault damage zone, where we have 900 fractures here. They all have different sizes. They're scaled to geological fault damage zone statistics. And if you include the simple linear scaling, we can model cascading earthquakes across these fracture networks. So we see earthquakes being able to trigger and slowly initiating a main fault rupture here, even though the main fault is not optimally oriented. So these cascading ruptures in off-fault fracture networks, they redistribute stresses. They can either assist or inhibit nucleation of large earthquakes, even if the main fault is weak. So for example, in subduction zones. We also have volumetric rupture that can occur entirely off the main faults. So here are some examples of this. I just go quickly through this. There's another JGR paper that has a lot of details. So this would be only the main fault rupturing and taking some of the fractures along for the ride, kind of the classical off-fault damage view. This would be cascading multi-fault rupture only in the fracture network. So this is, a volumetric earthquake just living in the damage zone. And this is the case that you've seen in the animation, where we start in the damage zone, and then eventually stresses are redistributed to activate a quite large earthquake on the main fault. These kind of models are only possible if we include the scaling of fracture energy with fault size. Otherwise, we will not be able to model all of these different earthquake nucleations sizes. Potentially observable, a couple of interesting features of these models. They have a slow rupture speed because you have all of this cascading going on. The focal mechanism is misaligned with the main fault. We have pulse-like ruptures, so the earthquake propagates as pulses through the fracture network. Very complicated moment rates with multiple peaks, high-frequency seismic radiation. Average stress drops are a little bit larger for cascading ruptures, and quite diverse off-fault fractures, which is something that might be linked to what we see from INSER and pixel correlation in terms of this heterogeneity of fractures that are being activated by large earthquakes. Any questions so far? I'm not sure I get to everything, but any questions so far about this part? Yeah?
It's very interesting. I mean, I read a paper, but I always had this question, the G prime. I never marked the G prime myself, but I measured stress drop, and I know how uncertain that is. And also, for fracture energy, I wonder, for seismic data, we cannot really tell, what is happening on the fault, what is, off the fault.
Right.
The whole volume that is changing is taking energy. So how do you think, the other explanations that may play here? Yeah.
Other explanations then, so more, it's a good question, but I'm not sure I have a quick answer for that one.
Okay, so
Yeah.
for G prime, I'm not sure if you track those, when you compile the table, do they give any uncertainty for the G prime measurements, or
No, but we know it's very large. Yeah. And, oh, sorry, all of these scalings are on log plots, right? So keep that in mind. Yeah.
Is it correct that the pre-stress in analytical model and numerical simulations are uniform? Rather uniform?
Analytical model, yes. In the numerical models, not. Because we have a regional pre-stress, and every of these fractures has a slightly different pre-stress then. So that is actually also, that was one of the questions we were wondering about too. But the numerical models prove that even with heterogeneous pre-stress conditions, this scaling holds. Because it's heterogeneous. All of the fractures get slightly different initial pre-stress depending on the orientation.
But am I correct that you're computing fracture energy of individual surface for a given large event, not individual smaller events?
Each of these fractures has its own DC or its own L, depending on its size.
Right. But
yeah. And then what I showed in the scaling is purely based on observations corrected with an analytical model. Then we ran the dynamic rupture models putting the scaling in, and then we back confirmed that the same scaling falls out numerically in these numerical models, which are more complicated too. So this is self-consistent in a way, but we're not prescribing the scaling of fracture energy.
What I'm wondering is that if you model individually these tiny events,
yes,
assuming the same conditions, in other words, no big events, but there's lots of tiny events.
Yes.
Do you get the same kind of relationship?
Yes.
As in,
keep in mind these are dynamic rupture models, but we can measure what happened in each of the ruptures of these small fractures in the purely volumetric models. I have the plots that show what you're asking, but they are not cycle models, right? So there's no interseismic period in these models. So that is something that is missing, and somebody should do that. Yeah. Yeah? 5 minutes? Okay. I do one more topic. This one, it's quick. Okay, actually this has no dynamic ruptures. I just want to show this because it's a very different representation of multi-segment complexity, and it links so nicely to one of the first talks we had in the meeting. So this is about the Noto earthquake, which was introduced before. One interesting aspect is that it's also generated a tsunami. Actually, early warning is working very well in Japan. 80% of users began evacuating before there was a tsunami warning even, but there could still be improvements. And I show you why it could be important to include multifold rupture complexity also for tsunami, early warning and rapid assessment. So there were two quick finite fault solutions published by the USGS, just as examples. The teleseismic one, which you see here, which had a lot of slip offshore, and then the teleseismic and geodetic one, which had no more slip offshore. And, but it incorporates additional regional GNSS observations. Now, what we did is a multi-CMT sub-event inversion. So what this means is that we're using teleseismic and regional seismic data to invert for not a single moment tensor, but for 6 of them in this case. The number is not prescribed, but it's continuously adding sub-events until the data misfit is reduced beyond the threshold. This is an MCMC approach, so we actually get 240,000 multi-CMT solutions as an output of this inversion. And what we see is that we have 2 distinct rupture episodes, bilateral rupture, 20-second delayed renucleation around the hypercenter. So you read this, here's the hypercenter, sub-event E1, E2, then E3, then we see E4, E5, E6. We see this as a southwest rupture episode and a northeast rupture episode with a 20-second delay. Now, what you can do with this, and what we did here, is that we translated the multi-CMT sub-event inversion into initial conditions for tsunami model. But before I get to this, I just want to say, going back to this reactivation, that it doesn't have to be a slow initiation phase. I think another arguable initiation mechanism could be reactivation, for which we already have fracture mechanics and dynamic rupture modeling explanations that have been tested before. So we use just Okada, elastic dislocation model, and regional fault system geometries that are available. Japan has a fault community model or fault model in this region to translate this multi-CMT into complex surface deformations that you see here. And this is the vertical fit. This is not the horizontal fit. It's the vertical fit, which is much harder to match, but important for tsunami generation. And important is that the peak vertical offshore uplift is up to almost 4 meters in the northeast of the Noto Peninsula here. a lot of uplift offshore. Horizontal fit, not as good, but the comparison, USGST plus G fit of the verticals here. And these are not finite fault models, just CMTs translated very simply into dislocations. Now we can use this to simulate the tsunami, which is interesting. We see, for example, wave crests that bend parallel to the coastline. We see a lot of refraction evaporations here close to the peninsula. We get it's small, but you can believe me, it's a very nice fit with tide gauge records, and especially the timing of the first arrival time, much superior than using the USGS models to model this tsunami. And then we don't only have one model, right? We have 240,000 of these. So we can also look into minimum offshore uplift tsunami models, maximum offshore uplift tsunami models, and can see the uncertainties there. And what we also did is that we took one of the science paper models by Ma et al. And used this to simulate the tsunami, and it's also, it cannot explain the tsunami as well because it doesn't have enough slip offshore. So the point is, tsunami observations can be helpful, while at the same time, multi-fault rupture could also be important, is also important to incorporate in things like tsunami early warning. And maybe I end with this. Why is there no dynamic rupture here? Well, the workflow to generate this operational for tsunami early warning centers is currently at the scale of hours, which is still too long, even without using dynamic rupture. We can speed it up to 15 minutes, but you know, this is the time scales that we're interested here in. And I had some more slides about earthquake early warning and so on, but I skipped these. But this is one of the applications where ML would be really important, or reduced thermals are really important if you're thinking about rapid response, early warning, and these kind of applications. So thanks for listening.
Just to clarify, it's not like you do one point source and then you update, and you actually put a new point source until you.
Yes, we're adding more and more sources until.
But you add them at the same time, and you invert everything at the same time.
No, you're going.
Sequentially, the risk is that you get the.
No. You first start with one for the full duration, and then you're adding until you're reducing the misfit.
Okay, right.
Yeah.
Yeah. So what is the northeast end of this channel?
What is that?
Yeah. How extend to the northeast of the rupture? Northeast side. Yeah.
It's here. And I have a comparison here to the survey sites in terms of uplift. So, for example, we checked for all of them. Can't really see this, but there's a lot of. You saw these pictures of people measuring the uplift. So it matches this quite nicely, and I have a plot also comparing these faults here with the fault model in the region. I can show you. So it's here yeah, and here.
Can you explain the tsunami amplitude at Kashiwazaki?
So this one of the stations is very tricky to explain because there was a landslide that we didn't model. I think there was an additional landslide that we're not modeling. So one of the stations is clearly affected by additional sources. Yeah. No, no, sorry if I didn't explain it clearly. So the point of that was that we developed this simple linear scaling of fracture energy with rupture size or fault size. And then we're using that scaling to assign the fracture energy or the DC or the L for each of these fractures, depending on their size. And then we see this cascading behavior, and then we analyze it, and we see it looks realistic, and we're doing all of these inferences. Yeah.
Thanks a lot, Alice, for the presentation. So I'm the annoying guy who collects the data on the chip. And although I understand that these are dynamic models, and that for dynamic models they fit the data perfectly well.
Not perfectly.
Well, yeah, that's where I'm going.
Yeah.
I actually think that they don't. So what is the room for improvement? Is it the inversion? Is it the physics that is too stiff for what you're trying to fit? The physics is not complicated enough, or it's not flexible enough, or is the geometry not correct? I mean, what is the direction that you would take to actually make it up to our data?
So for many of the observations we have, we actually don't need very complicated physics to match it. Like if you're just interested in matching, for example, the data we have for Ridgecrest, for Turkey, we show that the first order, you need to know the fault geometry, the regional tectonics, very simple frictional, you match a lot of observations without including all of many of the interesting things we talked about. So we do need other observations that can better constrain what actually happens. And I do have the hope that if we could do, for example, a dynamic source inversion for a range of earthquakes, and start to compare the outcomes more systematically, that this could be just throwing more data at this. But we're really looking from very far away. So actually, it turns out that we only need a few model ingredients to match many observations to first order.
But my point is that I really think that we already have these data. There's a lot of details that could be, a lot of things that can be considered as details in the data that are not. And when you compare the classic slip inversions with your models, there's lots of local differences.
Then are you sure they're resolved?
Yeah, where does that come from? That's I think, very important. It's a nice direction.
Mm-hmm.
Okay, we start here. Next speaker, Fabio?
Yeah. Sorry. Too long.
Thank you.
Try to put it around your neck.
Which is the right way? This
No,
one?
there's no around
There's
your
no
neck.
up and down. Like this?
Something like this. So we can better hear you.
Yes, this way.
Sounds good.
Here.
So there are many ways to approach earthquakes. So from lab experiments, rupture, dynamic modeling, observational, and Fabio is going to talk about analog modeling. Fabio is a researcher at the Center for National Research in Italy, and he's based at the University of Sapienza in Roma.
Yes,
All good?
all good. So, first of all, thank you so much, Anthony, for the great opportunity to give a talk here today. And the other special thanks is to some of my co-authors, Francesca Funicello, Giacomo Mastella, John Bedford, Elisa Tinti, Mattias Rosenau, and Adriano Gualandi. So the main goal of the presentation today is that one to provide you a blended overview of what's going on in the laboratory, and in particular in seismotectonic analog modeling. And yes, all the experiments that I will show you today are run at the Laboratory of Experimental Tectonics at Roma Tre University, actually. So to start, we have the experimental setup here. We call this experiment a Gelquake. It's basically a 34 by 52 plexiglass box, which is including a 10-degree dipping flat subducting plate, which is kinematically driven by a stepping motor that is below the experiment here. The wedge is made by gelatin, so we studied a lot the rheology of this material in order to have the proper scaling of the experiment. And the asperities are provided by gelatin against sandpaper interface. In this particular case, the experiment includes two twin asperities with the same properties that are separated by gelatin that is touching a plastic sheet. So what we are having here is that the depth range and the size of the two asperities is not subducting while the subducting plate is going down. I will show you a movie that that shows this more precisely. And as you can imagine, everything is quite much more simple than in Alice simulation. So we can just 3D print and test our ideas in the laboratory. So for example, we can 3D print a seamount-like shape, or prescribe what kind of roughness that we want on top on an undulated surface, as in the study by Irene Menichelli and Eleonora Van Rinsingen. So the gelatin is transparent. We have the opportunity to look inside of the experiment. So you see here 2 video cameras. So one is looking at the entire model. The other one is zooming on the seismogenic zone. And this is what we observe during one experiment. We have the subducting plate that is going down, and there's glowing particles that are passive markers, 50 micron in diameter, that glows when an ultraviolet light is shedding light in a cross section far away from the boundary of the experiment. And this is what we look at, what we see during one experiment by looking at it from top view with a similar acquisition. I will come back to, in the next couple of slides, I will come back on the details of the monitoring of the experiment. And in this video in particular, we saw with the background shading the trench parallel component of the rupture, yes, and with the black contour is the trench orthogonal component. We see sometimes that the two aspects interact, so they are somehow synchronized, but then at some point it comes a single asperity rupture, and then the experiment continues with such time of somehow quasi-periodic recurrence behavior that is observed. So this experiment takes almost 1 week to run one experiment, have the data, and so on. So we tried to speed up the modeling by building foamquake. This came out a couple of years ago in a paper by Giacomo Mastella. The experiment is wide bigger. It's 1.5 meters by 90 centimeters. And it's also quite flexible as a gel quake. And in this case, instead of having the gelatin wedge, we have a foam rubber wedge. And what is interesting is that the experiment features a 1 centimeter thick analog of the gauge that is made by sand and jasmine rice. So jasmine rice is super cool to work with in the laboratory because it stick slip at very low normal stress. So you can feel at the supermarket. If you push the jasmine rice, you hear the sound of the stick slip. So we have also the twin asperity configuration because we like frictional segmentation, lateral frictional segmentation at subduction zone. So now about monitoring, yes. We have implemented this analog of dense geodetic network using particle image velocimetry. That is that for each photo that we take from the experiment, we run digital image correlation, and we provide a vector field, in this case characterized by landward motion during the interseismic phase and seaward motion during coseismic phase. A typical time series look like this, so you have almost nothing happening in these cases where you have the analog of interseismic, and then you have sometimes the analog earthquake, sometimes the velocity profile is quite clean with a single peak, or sometimes the peak is more complicated in the case, for example, of double asperity rupture, as you can see here. Sometimes it's also very complicated, but you have a single asperity rupture, so this can be analyzed more in detail. So since for each experiment we have like 10,000 of frames, I thought this is the perfect playground to apply machine learning. So actually a friend of mine suggested, why don't you use machine learning to work with your experiment? So we took all our 1,500 synthetic GPS stations. We extract statistical feature from the time series that you can see here. I can go more in detail how we did that. Then I created a gradient boosting method, a gradient boosting machine learning model to predict which is the time to failure, and I used two different framing. I use a global framing, which is a time to failure all over the experiment, so meaning that each of these points can fail in the future, or time to failure at 9 different points distributed along the margin that are highlighted here by the blue dots. So the results look like this. We all became familiar with time to failure that is decreasing, approaching the next earthquake. That is the red line here. And prediction, as you can see, it works so and so. Here you have the relative root mean square error for comparison. But if we extend this type of analysis in space, you got this type of representation, which is quite messy, but here is a zoom. You have very low predicted time to failure, and with red the failure that occurs really. So machine learning works pretty well with predicting not only the timing, as Yoshi Kaneko said during the first day, but implicitly also the size of the rupture. In this case, was saying, okay, the asperity to the north will fail, and in this case, machine learning suggests that both asperities are going to rupture very soon, in less than 2 seconds. So machine learning has great predictive potential given a dense geodetic network and very long time series. This was another crucial point I think that Yoshi said at the end of the presentation. The second exercise that we have done was trying to understand why and where the information was coming from and why the machine learning was so successful. So I used binary classification framing, that is next period an alarm, so an imminent event analog earthquake will occur or not. And I used the sequential feature selection that is quite common used in machine learning analysis in order to provide an idea of which is the feature that is really providing a positive forecast for the future. And in particular, in this case, which is the station that is giving me the opportunity to successfully predict the next earthquake. And this is done for the different purple target point that you see here, the same 9 target point. And if we take all this data in ensemble, okay, we got this I'm sorry about this. So, oh yes. So that is, maybe somebody of you already know this, but for me it was completely unconditioned information. So it is the deepest part of the asperity that is where the information was coming from. So, and this is almost if we scale the experiment, this is about 70 to 80 kilometer wide band parallel to the coastline. That is where we should look at. So Giacomo Mastella, a PhD that made the studied at Roma 3, made a step even further, and he tried to predict not only the time to failure, but he used the computer vision to forecast which will be the map of velocity in the future, at different time steps in the future, okay? So what we see in this slide, I know it will become a little bit messy, so it's better to explain correctly. We have a time that is going on this axis. Each map is one frame, and we have a bluish color for landward motion, red color for seaward motion. So we have interseismic, 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 deep, slow onset of the rupture from the base of the, area close to the backstop of the experiment, the right asperity that is failing, then the rupture grows, the left asperity is failing, and the analog earthquake end here, okay? So if we want to forecast the next event, we are at a prediction horizon 1 equal 1, meaning that we are at this stage and we want to predict this other frame, okay? we see that machine learning is doing a great job. So also a reddish color is starting at this moment, predict the rupture starting from the right and growing toward the left of the experiment. So it's capable to do everything. I was really impressed. It's a remarkable result in my opinion, this one. And finishes with a little bit of delay, as you can see here. So we can do the same game for prediction horizon 2, 3, 4. And as you can see, going down, the picture of forecasting became more blurred. Like as we can do with weather forecasting, for tomorrow is okay, for the day after tomorrow, so and so. And what is very interesting, we can talk about this, is that the prediction horizon is roughly the same as from quake duration. In fact, here on this line, you can see that that computer vision is no more capable of saying, okay, there will be an earthquake. Okay, so far so good. We went very far with machine learning, but we don't have such long time series that are available in nature. So how to apply this strategy with real Earth data? And here I'm trying to do the exercise of trying with a single map to see what is going, what can we say. So the idea is, can we use large mega earthquakes to probe the seismic cycle timing of neighbor and ruptured subduction segments? And this idea came after a paper by Daniel Melnick, who explained the super interseismic period, and probably somebody before Daniel, or let's say. And so what is interesting here is that this map is showing the acceleration of geodetic site, and we can see that at Hokkaido Island, the landward motion is going to accelerate from the moment of the Dogo earthquake and to the following period. So it's a coseismic acceleration, it's not a post-seismic one. And Hegietta and Ugeradi investigated this type of acceleration, not only for Tohoku, but also for Maule, Tokashioki, Ikike, Otsaga earthquake, and they all show this accelerating pattern, right? So, which is very interesting, and I thought, oh, could it be that this pattern is informative of something? And then I went through the literature, and I found that in Sumatra we have this beautiful coral microatoll that are paleogeodetic sites. And basically, they record the subsidence or uplift as a response of the seismic cycle on this margin. And we can see that during the Mentawai earthquake in 1797, the neighboring island of Pangai has been subjected to a reduction of uplifting, interseismic uplifting in order of half. So there have been different hypotheses for explaining this acceleration of the acceleration, so I'm not really an expert, but I can tell you what is going on in the laboratory. So I took again one experiment with predominantly single asperity ruptures. So we have time, distance on this plot. Blue is landward motion, brown is seaward motion, and we analyze the different cycles. So we have this single asperity ruptures, okay. So we focus on this tiny interrogation window here that is exactly at the middle of the neighboring rupture timing. Of course, we have not used only this time window, but also smaller and larger. And we keep track of this, that is timing of interaction, okay? So remember this delta t is timing of interaction. How much time is between the cycles of the two neighboring segments. So we have all the range, in the laboratory, all the range of deceleration, in this case, a huge deceleration, a smaller deceleration, an acceleration, and a very big acceleration here. So we have delta t, that is the timing, and delta v, that is acceleration or deceleration of the geodetic size of the neighboring segment. Perfect. We now look at these two extreme cases. In map view, we have this funny twisting behavior. We call it this twisting. The background shading here is the rupture of the southern asperity, and this is the velocity that is occurring at the moment of the rupture. So you can see that we have this type of behavior occurs when we call it early interaction. The receiver is unripe, the earthquake cycle just started, and the landward sites, that is here, they are forced to go landward faster than before the neighboring earthquake. And here is the opposite case. You see that the velocities are now toward the seaward, and in fact, this occurs as a late interaction, and it's happening when the gelatin is already completely squeezed. It cannot squeeze anymore, even if there is a neighboring earthquake that is occurring, and the twisting in this case is confined in the offshore region. And so we observe in this case a landward deceleration of the geodetic sites. So since I tell you before, we can take track of which is the timing of interaction, and associated to such a velocity variation, we found this type of relationship. So basically, we have a negative. We observe that a negative interaction occurs very late here in this area of the cycle of the receiver patch, the northern asperity, let's say. And also that this occurs independently of the velocity of the triggering asperity. So if the neighbor rupture is very, very fast or very, very slow, nothing changes. You can see this with the color coding on this graph. And also that there is quite a wide range of variability here in the middle of the seismic cycle duration, meaning that we can expect a little bit both acceleration or deceleration. And now I try to make the assumption that Tokashi Ogi occurred only 3 years before the Tohoku earthquake, so an acceleration was somehow expected according to this model. And in Sumatra, paleoseismology tells us that the previous large event occurred somehow in 94 years before the Mentawai Island earthquake, meaning that it's late in the cycle. So natural cases, even if are only 2, seems to match this kind of picture. So in this case, analog model has been useful because they allowed us to use a peculiar twisting pattern into a precise moment into the seismic cycle clock of subduction zones. Yeah. Yeah, I feel that like this. Perfect. And now I would like to stay to natural cases application for analog modeling. We have we have the Valdivia earthquake here, 1960, and Maule earthquake here, 2010. So they are very interesting. Have been recently studied in this preprint by Aedo and co-authors. And in particular, with particular focus on a little island here, Isla Santa Maria, and where new paleoseismological data is available based on coastal geomorphology. So the authors of this study found that large ruptures, characteristics like Valdivia earthquake, they occur more periodic than smaller ruptures. Okay, this is what paleoseismology tells us. And also what is interesting is that in the case of Isla Santa Maria, we have this bimodal recurrence time that is going on. So please remember these two numbers, that is a coefficient of variation of recurrence time. 0.5 means quasi-periodic, 0.66 is less periodic than the other case, and coefficient of variation for who is not into the subject is given by the standard deviation divided by the mean of the recurrence time, and tell us about periodicity, right? 0 is perfectly periodic, 1 is a random process. So we tried to model this kind of setup in the laboratory. We used one big asperity close to another smaller asperity, and we kept the normal load on top of one asperity fixed while varying the other, or vice versa. So we kept the normal load of the large asperity fixed and varied the other. So this is how an experimental data look like. With foamquake, we have a beautiful stick slip for the large asperity, that is the green time series here, and the smaller stick slip for the small asperity in this case. And you can see here for this slip phase that corresponds to a small rupture of the small patch, or a very big rupture in this case, where you can see that both time series drop. Okay, Elia Latipova, that is a PhD student working with John Bedford, analyzed systematically the recurrence time of this time series, and she found that the two asperities are way more periodic than the barrier. So what is going on in the middle is somehow filling the events that are coming in from both sides. And also that the short asperity shows this type of bimodal, or maybe, I don't know, this is very small with respect to the other, but we have maybe period doubling also in this case. And the barrier is showing higher coefficient of variation. This is for a model where we have the same normal load on the two asperities. And this is for a model where we kept a much larger normal load on the large asperity with respect to the small one. And we see that the large asperity is more periodic than the small asperity. So we need, okay, so barriers display a complex behavior. We have period doubling for the short asperity. And if we add the normal load, meaning that the asperity must be larger and also stronger, we can also model this type of more periodic and less periodic neighboring asperities. So I have 6 minutes, right? Okay. Less. All of this story yes, is based on scaling. So maybe many of you worked with scaling, and we also tried to constrain our models in terms of this theory that is called the theory of scale models applied to the study of geological structures, which basically says that if you want to shrink your model, you also have to use weaker materials, in few words. So, and what I really wanted to do this time was to try to frame a laboratory experiment into the rate and state formulation, just to say, okay, we have something that's stick slip and the properties are similar to other type of modeling. So I used CUDIN and I linked it in together with the simulated annealing, which is an optimization algorithm that allows us to retrieve A, B, and D sub C independently. So this is each of the 3 parameters are free to vary, while testing how our simulation going with respect to recurrence time, rupture duration, or displacement. A global minima will be in the case where we have all the 3 parameters that are fitting properly. This is how the simulation is going. So we have the error, the number of iterations of our loop with CUDIN, and in particular we have this one-dimensional model, and you can see that we have time, displacement. Simulations are getting closer and closer to the real data, that is the green line here. At the end, we are able to retrieve A, B, and D sub C of our analog model. And it won't be very difficult for me to convince you that, okay, we can perform quite well. We have such a rupture. This is time, distance in the laboratory, which is propagating somehow bilaterally. And also in CUDIN, we have the same type of behavior with the same axis, same scale. So I think we have the opportunity to repeat the same exercise for asperities of different sides and retrieve again A, B, and D sub C for different sides of the asperity. And what we found is that this important number is the Ruina number, which is proportional somehow to how critical is our fault, is close to 1 up to 3, 4, let's say. And while RB is decreasing with increasing the size of asperity. And I would like to reach the end of the presentation with this slide, which is a plot provided by Sylvain, which shows the peak velocity as a function of the Ruina number. And we have periodic short-term slow slip event when the Ruina number is very slow, very small, sorry. The peak velocity is increasing, and then we found this period doubling behavior and the transition to Gauss before reaching a periodic fast regular earthquake, let's say. So according to what I found so far, analog experiment, they have this range of velocity, 10 to the minus 2, 10 to the minus 4, and Ruina number smaller than 4. So I thought that, okay, they fit this part of the graph. So smaller Ruina number is consistent with symmetric bilateral rupture propagation from the center of the asperity. But then if we zoom on this area where we have a larger Ruina number and toward the period doubling, and we analyze the time of interseismic period of the previous event divided by post time of the following event. This is commonly done when you analyze a period doubling system. We have that sometimes we see periodic behavior, but the experiment try to jump to period doubling or half of the period, meaning that we have 2 times the recurrence time of the previous event. So we have done this for one experiment, but I ran a larger data set for all the asperity size that you saw before, and you still see periodic and period doubling, and then the picture became more blurred toward the right, which is increasing asperity size. And a similar behavior occurs if you read this image, reading it vertically. So we can kind of define 2 fields, periodic and period doubling field in this part of the graph, and agogic behavior. Here you see that none of the point is fitting on the one line. So I think this transitional behavior is very interesting, and this is where I want to put my effort in the future. Thank you so much.
Hi. For your talk. I wanted to go back to the beginning when you were trying to forecast the foam quakes.
Yes.
But you showed that if I understood correctly, you showed that the computer was looking primarily at the area just below the
yes.
Right. So thinking back to Ron's talk about the asperity shrinking
yes.
during the interseismic period, is it something that you see, and could it maybe explain why there's this going on?
Yeah. So something that I haven't said is that all we have done with foamquake is transparent, so we can ideally look at the bottom, but with foamquake is surface displacement. I've done, with the help of other colleagues, an inversion to look at how different is the slip map at the bottom, and is not looking that different because there is only 10-degree dipping and flat surface. So I only work with surface velocity, and I'm not sure if this surface velocity is enough for saying that we see this shrinking of asperity. And another important point is that everything is simple in the laboratory, so we can add station and remove station. What I show you is only the framing where we don't have the offshore, and it highlights this down deep part. But we can also add the offshore station and run exactly the same code. And in this case, instead of being aligned parallel to the coastline, we have 2 stripes that are matching the 2 asperity. Hi.
Thank you for the talk. I was wondering how sensitive are the results from the experiments to the boundary conditions, like the size of the box,
Yes.
for instance, the results on the twisting.
Yes.
Yeah.
Yes. This is a very good question. And so yes, in the past I tried to quantify this, at least for gelquake, because gelatin has sidewalls, and it slides on the sidewalls. The good thing of gelatin is that when you cut it, so you have a mold, you cut the gelatin, and it releases water where you got. So actually the sidewalls should be lubricated somehow. And for foamquake, it's a free, the experiment. It's not touching the plexiglass.
Yeah, thanks. Oh yeah, very impressive results. I'm just wondering, based on your final part of the results, your foamquake seems to be a large-scale slow-slip event. So
Exactly.
is it better to look at the interaction of slow-slip patches, and then you have a lot of histories and data, geodetic data to test these
Yes.
kind of models.
In fact, I haven't shown today, but so I've been working with Adriano Gualandi, who's master in this dynamics, retrieving the dynamics, and we have a very similar system dimension in the laboratory. So I thought, actually, it was one of yes, thank you so much for the comment. It was one of my conclusion, say that yes, it could be that these analog earthquakes are more similar to slow earthquakes than I have at least 2 hints. One is the small Ruina number, and the other one is system dimension. Hopefully the paper will be accepted soon. Yeah.
Yeah, thank you very much. I was wondering, like in your model where you show the interactions between asperities, you explain everything through elastic interactions.
Yeah, it's the only thing that can happen. So we don't have a fluid, we don't have
Yeah, sure. And so I was wondering, because there are some papers that proposed viscoelastic post-seismic flow to explain this type of interseismic, and there is notably a paper by Wang and collaborators where they propose a very weak lab below the oceanic crust. And so I was wondering whether you think that elastic interaction is enough. Is it, like, have you tried to actually compare with observations? Because you show observations, then you show the models.
Yes.
In terms of concept, it works, but does it actually reproduce in terms of seismic?
Yeah, this is
what would be the role of viscoelastic? Maybe nothing.
So what I'm showing and what Hegi is showing is that this behavior is co-seismic. So it's not post-seismically driven. So the change of the slope happen at the moment of the earthquake and keep going with the same slope. And John analyzed similar data again for Tohoku and for Maule, and he found exactly the same type of behavior. So if it was post-seismic, we should have seen somehow transient. And the second answer is that we don't have such a viscous layer,
sure.
So it can happen even if you don't have it. So.
Okay, one last quick question.
Yeah.
Answer, maybe?
In the context of earthquake prediction with machine learning, would it be possible to add in the real area of contact for the earthquake, for example? So imaging directly what happens and the things.
That would be amazing. So I don't know, because when you look from top view in the gelatin, you don't and with the sandpaper below, actually the gelatin is deforming and filling all the voids. So I don't have a white and black. And ideally what is good to do to track this real area of contact, is to have something that changes in the image. So I don't know if it's doable, But yes, this is a great suggestion. Thanks. Thank you.
Thank you.
Thank you.
The microphone.
Microphone. I will. So Quentin.
How do you do that?
Allora, I put it like this.
Ça marche comme ça?
Yes.
C'est de mettre un peu devant. Voilà.
Ouais, comme ça.
Go one time.
lose our jobs, business. So the talk is given by Quentin Bletery, who is a researcher at ERB, the Institute for Research and Development, and based at the Geodetic Laboratory.
Thank you. So, do earthquakes start with the Precursory phase of slow slip? If this is the case, and if you have GPS stations nearby, one thing you can do is calculate the displacement you expect from this hypothetical slow slip at the location of those GPS sites. If you do that, you will get this kind of red arrows here. But now if you look at the actually recorded displacement, let's say 48 hours before an event, what you will see is probably something like this. And if you look 1 hour later, it will look like this, and so on. It will look rather chaotic and not at all like what you expect from this hypothetical slow slip, just because if there was an obvious signal there, we would have seen it by now. So what we've been looking for is a much more subtle signal, and the way we've been doing that was by calculating dot product between the expected displacement in red and the recorded displacement in blue. So one thing you can do is calculate those dot products and sum them all at a given time, and that will give you this point here, which is just the sum of all these dot products at a given time. Then you can go to the next time step and do the same thing, and so on, up until 0, which will be the time of the earthquakes. And now the idea is that if there is nothing to see, that means that the dot product is equally likely to be positive or negative if it's completely uncorrelated. So what you expect to observe is a cloud of points more or less centered around 0. But now, if there's something to see in the data, like an acceleration of slow slip leading up to the rupture, what you expect to see is something like this, which will slightly go up as you get closer to 0. Now, another thing you can do is not only stack on all the GPS stations, but also on all the earthquakes. And this way, well, hopefully you can get a clearer signal. So that was the idea, and basically we applied that to all the magnitude 7 and plus earthquakes that we could find. And that was, at the time, a total of over 3,000 time series recorded before 90 events. The data come from NGL. They're processed at 5 minutes. And if you do that on all this data, here is the result of this global stack of 3,000 GPS time series recorded before 90 earthquakes. Here's what it looks like. So you got time here, that's 48 hours of records. 0 is the time of the earthquakes. So each time series has been cut at its 0 and then stacked, basically. So what we can see is that we more or less see a cloud of points centered around 0, except in the last 2 hours, where it's, I would say, subtle, but it does look like consistent with the idea of accelerating slow slip towards the rupture. But it's still rather noisy, so one thing you can do is to get rid of the remaining noise is to apply a moving average, and if you do that, you will get this red curve here. And one more thing that we are going to do is define this error ratio between the last point of this moving average and the maximum of this moving average on the rest of the time series. And here, that value is 1.82. So now, the next step is, well, how often would you see something like this just looking at random time windows at any time? So that's what we've been looking at on 100,000 random time windows. And each time you can calculate a stack and then calculate this error ratio. And here's the distribution of this error ratio that you obtain. And this is the value that you get before the real earthquakes. So you see that it's kind of outside of the distribution, which means that it's not super often that you get such a signal. And actually, we can answer that question, how often would we see something like this in random time windows? The answer is 0.3% of the time. So now the question is, where does this signal come from? So in the original paper last year, our interpretation was that it's indicative of a potential acceleration of slow slip leading up to the rupture. But since the publication of the paper, I would say that counter proposition have been made. A very popular one was that the signal would originate from common mode noise, and we will see that in detail. Other proposition has been that a possible contamination by a co-seismic signal could have produced that signal, and also it's been proposed that it could be due to foreshock preceding at least some events. So let's start with common mode noise. So what is common mode noise? It's noise which is highly correlated in both space and time, so more or less common across all the stations of a given network. There's no real standard way of estimating that, but what people usually do is calculate the mean of all the time series and then remove that mean. That would be an estimation of the common mode. So if you do that, you go from this stack. If you do that for the earthquakes for which you can do it, which means you have to have at least a good amount of stations. So restricting the data set to the events for which you can do that, you go from this to this once you remove the common mode, and you can see that the signal vanished here. And it's even worse than that, because if you take the common mode that you calculated and apply the stack on it, here's what you get, and you get the impression that all the signal comes from the common mode. But now the question is, what's the likelihood of getting something like this just before the earthquake, right? And actually, we had an estimation of that right before. It's 0.3% of the time. So there is an apparent contradiction here. So one way to resolve that contradiction would be to follow that potentiality, which is that removing a common mode this way might actually remove a true tectonic signal. And that's something you can test just by doing a syntactic test. You impose a synthetic tectonic signal right before all the earthquakes on the faults, calculate all the synthetic displacement at all the GPS stations, and then you have to add noise. And the best choice of noise is empirical noise, so noise that you're going to collect on your stations. And the best window to do that is the window 23 hours and 55 minutes before the event, just because satellite orbits repeat every 23 hours and 56 minutes, meaning that the noise will be as correlated as it can be between time windows offset by this time element. So the interest of doing that is that now you can remove the common mode and see the effect on the stack, and you know what you need to compare it to. That's the target denoise stack. Since you imposed the signal, you know what you're supposed to find. That's the target. That's what we should find once we remove the common mode and do the stack. And same thing with the noise. We impose the noise, so we know the noise. So we know what we should find when we do the stack of the noise after the correction of the common mode. And if you do that, here's what you get. So that's the stack after removing the common mode. So we can see that there's kind of a signal here, but it's not where it's supposed to be because we impose the signal to be here, not here. And what you see here is that the signal actually appears in the stack of the common mode. And it's more obvious if you look back. Really, you know that this spike here doesn't come from the noise, because once again, we know the noise, we imposed it, it's here, and it's not there. Actually, it comes from there. And actually, this spike here doesn't come from the signal, it comes from the noise. So what it tells us is that it's just really difficult to discriminate between common mode noise and a subtle tectonic signal. It's really hard to make the difference, at least this way. So what we can say now is that removing common modes, at least this way, may definitely remove a true tectonic signal. And wrapping up, looking at random path time series says that it's fairly unlikely that a common mode would produce something like that. But there are other ways we can test the consistency of this signal, and one way is to look at it spatially. So one quick thing that you can do is to move the source around. So when we calculate our Green's function here, we assume that we know the location of the future earthquakes, and what happens if you move those locations. So we are going to calculate no Green's functions here that are associated to a new location. So if we do that by moving the location, let's say 200 kilometers away in all the direction, here's what you get, and you can see that there is no signal anywhere here. Then you can get a little closer, 100 kilometers, northwest, east, and south, still no signal. you can get even closer. At 50 kilometers, you start to see some patterns here and here, but it's a lot less obvious than at the actual location of the upcoming events, which is those ones. I'll just play it backward like this to see. Anyway, so you can generalize that test and do it for any location on a grid, which is 50 kilometer spacing. And for each location, we are going to calculate our air ratio, and this is what you get. And actually, the maximum value is at 0, 0, meaning at the location of the upcoming event. And it's quite difficult to reconcile that with the idea that this would be due to common mode noise, because it's not supposed to point to the location of the future event. And in a way, it's also pointing to the time of those events. So what about co-seismic contamination? So one quick test that we can do is that, so if you think about it, if that signal comes from leakage from the co-seismic offset, well, we can replace the Green's functions directly by the co-seismic offset. And if the signal leaks from the co-seismic offset, then here it should become a lot more obvious, right? Because you're just correlating something which is already correlated. So if you do that, you go from this to this, and you can see that there's nothing there. So I don't think it really comes from the leakage. And actually, the reason why I think it's probably not that is because it's not because of that. It's because I talked with the NGL people, and they don't think that it's really a possibility. So if we wrap up, so where does this signal come from? From what I told you, I would say that the hypothesis, well, the proposition that it comes from common mode noise is not super likely. Contamination by co-seismic signal, I don't think it's very likely either. I didn't talk much about foreshocks, but actually a quick response is that the equivalent magnitude of this signal is on the order of magnitude 6, and it's just impossible that we miss magnitude 6 events before each earthquake. So I don't think that's a possibility. So that leaves us with our original interpretation, which remains, at the very least, I think, plausible. So I'm just going to finish with a quick update. So this was the relative contribution of all the earthquakes, the 90 earthquakes in the original paper here. But since we published that paper, there were a bunch of new earthquakes. And so if we update with these new earthquakes, here is the new repartition of the weight. And you can see that these earthquakes count a lot because they add 2,000 time series. Because each time there is an earthquake now, there is a lot more data. So it's a kind of an exponential curve. And so adding those new events, we go from this stack that we've been seeing all along with an error ratio of 1.8 to this one, which has an error ratio of 2.1. So I don't know how well I'm with time, but I'm going to stop here. Everything has been written in this preprint, which has been sitting in Seismica for quite a bit now. Take the advantage of having the whole Seismica board to say that. And yeah, and I'll be happy to take any question.
Yes, I'm a little confused by the way you remove the common mode. You said that to take the average from all the stations, right?
Yes, by seismic network. Yes, greater than some distance, 200 kilometers. I just replicated. I just replicated what Kyle and Judith did.
Okay, because the way we do it in my group, we do an ICA on the time series, and then you take the mode that is a rigid body motion, and then you can keep the station data nearby. But if you remove the distant station,
well, you can do that when you have a clear signal, but here at the scale of each individual dual event, we just don't see anything. So when you do an ACA, well, you see a bunch of things. You can't really identify any components.
Students, postdoc? Yeah?
So, I mean, I said this is a real precursory slow sweep migration. And, you know, if I think about like the observations I know, like from Seismicity evolution or from like Cargèse paper, I think they can last longer than just like 3 hours. Like if I project a line to the time series here, it's like 3 hours, 4 hours, you know, things like that. So I'm just wondering, like,
Not sure I understand what you mean. The time constant is on the order of the hour, maybe 2.
So like if you go back to one slide,
Yep.
from the time series here, like you start, just that slide, yeah, this
Yeah.
one is good. So like you have this, increase of the stack.
Yes.
Like you got to project that to like a time before the earthquake, it's like 3 hours.
That's already, so this is hours, this is the time of the earthquakes.
Yeah, this is the time of the
So
earthquake.
the time constant.
She's asking if you do the same analysis for time scale of weeks or months, because that's
No.
where a few transients happen.
Right, right. So, I mean, because the observations were saying longer time scale for these slow events, right?
So the quick answer is no. And the reason for that is that when you take longer time windows, you start to have gaps and offsets due to many, many things. I didn't know how to deal with that. So I'm rejecting everything which has a gap and an offset. And so if I take one more day, I basically don't have any more data. I did try though with daily data on longer time windows, and I didn't see anything.
Thanks, Barry. Can you go back to one of your slides about common mode? Because I also had a question along the lines of it looked like, I would expect after you take the common mode out that the numbers would decrease, but they look like they increased.
The number, here?
Yeah.
So this is original stack. That's all the same scale, right? Yes. So
You showed several things where the numbers were actually bigger and after taking out the common.
yeah, so that's because that's the synthetic test.
Okay.
So here I'm imposing the signal, and also I'm restricting the dataset to 31 events for which it's possible to calculate the common mode. So that means there is a lot less data here than in the original stack.
These numbers are not normalized by that?
No, nothing is normalized. It's just what it is. But so you're right. This is less noisy than that, and in a way that's normal. You're removing common mode, so you're lowering the noise level, and the noise is supposed to be there.
But that shows that the signal you have it at the stations that are more distant than 200 kilometers, right? Otherwise,
Yes.
it's not true.
Yes, definitely. Well, it's more tricky than that. Part of the signal, you see it far away. It's, yeah, so what, yeah.
So if you expand, then can you make the area that you discard calculated common mode larger?
Yes, but at some points you don't have many data left. Well, you still have, yeah. No, and yeah, I played with that, and it doesn't change much the results. You usually see the same trend. Basically, what it tells us is that when you have a very, very small signal, it's really hard to extract it by trying to estimate the noise this way. Because so you have the common mode, but you also have some random noise on top of it, and that's making the problem complicated.
So could it be an artifact in the recalculation of the orbits? Because of the co-seismic displacement, when you calculate the orbits, there's a smoothing, right? And so it smooths the co-seismic.
According to Jeff Blewitz and his rough calculation, the order of magnitude that of the signal it could produce is orders of magnitude below what we can see. So it doesn't think that's possible.
Really nice to see this exploration of this really intriguing observations. I didn't quite understand the histogram that you showed with the 23%. Can you explain that? And I have a follow-up.
That one? So that's the distribution of the A ratio that I defined just before, which is the ratio between the last point of the moving average and the maximum of this moving average on the rest of the time series. And what we do is that, so we take 100,000 random time windows, we calculate the stack out of those. Then we calculate the moving average, then we calculate this error ratio. And what I'm showing here is the histogram of this ratio. So there's 100,000 R here, which correspond to 100,000 stack of random noise, basically.
So those are 100,000 random time windows that are not specifically that 50 hours, but lots of other times.
Yes.
Okay.
And actually, I don't even bother about removing earthquakes from that. I just take random time windows. So it's actually quite possible that you do have earthquakes before some of them.
Yeah, like with this kind of analysis where we see something just before an earthquake, looking at a very short time window, the question is always, okay, we see something that looks anomalous. It's the only time in this 50 hours that we see something that goes up. But how anomalous is it in the grand scale? And that's what I'm
Yeah,
how much you
that test was meant for that.
So I was wondering, when you compute your synthetic wind function for the stack, what size do you assume? Is there a specific size of the dislocation? And same question for the synthetic test that you do?
Point sources. Point sources.
It's a point source in those cases.
Well, actually, I take 1 kilometer large subfaults, but what in my
So I'm just surprised in the synthetic case that you, even though you apply point source, you still see it in the common noise at
yes. So obviously, I tried that with larger faults. I don't really like to do that because you have to look at each event, and actually you have no clue sometimes where is the fault and how it's dipping. But so if you make the fault larger, obviously that's even more obvious. Like you would actually put everything in the common mode.
So I didn't really understand how you generated the noise stack that you're using for the other one. Because
so
the way I would have proceeded would be to characterize the noise of the time series that you extract, generate 100,000 random realization of these, and then have the probability density function of the actual acceleration that you get from these thousands of realizations of noise. But if you have only one realization of noise, it's only valid for this realization of noise, which is statistically not.
So the test you're talking about, if you go to the preprint, you actually have it. We did it, and it's the exact same result as what I showed. So either by generating those realization or by taking random time windows, you get the same results.
So now you use the 40 hour, 48
yes.
But if you use a more longer with the 1 hour or more longer timing, how does this distribution algorithm?
Okay, so that's what I was answering before. So the reason I'm not doing that is because I'm kind of selective in the time series I take. And so if there is an offset or a gap in the time series, I exclude it. And if you keep those rules, if I had one day, I lose half of my stations. If I have had 2 days, I lose even more. And at the end of the day, I just don't have any stations. Especially because at some point, you're going to get to the foreshock of the Oku, so you have to remove everyone. Yes. Well,
in your old and updated selection of earthquakes, how many of the earthquakes contribute positively to the increase? Is that something you can
yes, I
define?
remember that I did that because you asked it at some point. So I'm trying to remember. I think it was 75% or something like this, which were contributing positively. I would need to check those numbers.
So there was the number of events which are already contributing.
That positively contribute to the signal that, because at the end, some events will go down, some will go up.
Yes.
Actually, I remember now. So it was almost half-half in numbers of events for the original dataset. I don't think I did that for the update. But in terms of number of observation, it was 75, 25, something like this.
because in the pie chart you show at the end, you seem to have like a equal contribution by many events, but in the end...
no, it's not at all equal contribution.
Because in the pie chart you count the number of GPS stations, or you count the number of...
So it's the weight given by the Green's function. So obviously it's related to the number of stations, but also to where the stations are. If you have just a few stations but very close, that will count a lot. That's actually the case of Nicoya here.
Right, so you could label these now with, helps confirm the result or not.
Helps what?
Well, positively contribute.
Yes, yeah, I could recalculate that, yeah.
I have too many questions.